So, hello and welcome to this webinar on ARM Mobile Studio. I'm Pete Harris. I'm the technical director for the Mobile Studio product, so I own the technical roadmap and kind of delivering this out to our customers. The aim of this webinar is to give you a kind of 1 hour introduction into sort of the technical workflow that Mobile Studio enables and the tools that you will get as part of the Studio package. So we're going to look at what is Mobile Studio. As an application developer, why should you care? Why should you download it? Why should you use it? And what are the tools you are going to get in the box? What workflow does Mobile Studio enable you to follow? How will you optimize your application? And within that, there are a number of components that you might then want to go and look at. So it's a software optimization tool for profiling and optimizing your software applications. It's a GPU profiler for optimizing your rendering applications, and then you can dive into your graphical applications in more detail to look at the API behavior and the shaders that you're using and the performance of those. Finally, we're going to look at one of our new tools that's in development called Performance Advisor, which is looking to automate more of this workflow to help people embed this inside their continuous integration process. And then at the end, we'll have a very quick look forward at what's going to be coming up in the next 12 months. So first up, what is Mobile Studio? So it's a set of performance analysis tools for ARM IP, covering both ARM CPUs and ARM Mali GPUs. It's designed for Android application developers, so profiling and optimizing applications on released phones that are in the market today. And the focus is therefore on ease of use, so you don't have to be a silicon design expert or a phone design expert. And the tools are designed to work on non-root phones. You don't need to have a special device to use these tools to profile your applications. As ARM, we develop a lot of the IP that goes into these devices, so our tools can provide rich data about what's going on inside the phone in terms of CPU behavior, GPU behavior, memory system behavior, if the phone exposes any analog events such as thermal sensors. So we can help application developers move beyond simple time tracking or frames per second tracking to look at actually what's going on inside the device in a bit more detail. As an application developer, why should you care about optimizing your application? The most important one for high performance applications is about user retention. So if you're a game developer, we have data from our game partners that shows if you can provide a smooth user experience, no frame rate hitches, a long battery life, then you're more likely to retain users over a 30 or 60-day period. And retained users who interact with your games regularly are going to be the users who are more likely to pay you money. So this is a good thing to aim for. In addition, optimization is critically important for mass market devices. So if you want to widen your target market, ensuring that your application runs smoothly on mass market phones, not just the latest high-end phones, it is a really important thing to do. And it's those mass market phones that are going to have some more of the performance issues because they have a lower specification. In addition, for AAA content, where you're really trying to push the graphical envelope, you tend to be pushing your device to the limits in terms of the performance you're trying to get out of it in the available power budget of a mobile phone, which is about 2.5 watts for the whole system. So if you want to really squeeze the highest quality visuals out of that device, you really have to make sure that you're using every joule of energy as efficiently as possible and making sure that those effects are really justifying their energy cost. In terms of why should you care about our tools in particular, a huge amount of the mobile phones in the market are based on ARM technology. So over 95% of the world's smartphones are based on ARM CPU technology, using either processors built and designed by us or processors using our architecture but built by our silicon partners. And in 2018, we shipped over 1 billion Mali GPUs into a wide range of markets, including smartphone and sort of Android DTV. And for some of the newer technology, things like dynamic heterogeneous symmetric multiprocessing, we have energy efficiency technology in the design that lets you load balance your software across high performance CPUs and high efficiency CPUs And tools such as Streamline can help you look into the device and see how the software workload is being split across those processes to make sure you're really getting the energy benefits that you think you should be getting. So what do you actually get in the box? So Mobile Studio is really built up of 4 tools. Today, 2 tools ship in the Mobile Studio release that we've just made. Streamline, which is a system profiler, and Graphics Analyzer, which is an API debugger. And we'll look at these in a lot more detail over the coming slides. In addition, there are 2 support tools which are available. So Mali Offline Compiler is for profiling shaders running on the GPU. It's kind of part of the workflow that Mobile Studio enables, but it's not currently shipping in the Mobile Studio bundle itself, but it is available on our website as a separate download. We have a beta tool still in development called Performance Advisor, which will be part of Mobile Studio in a future release, which is looking to tie all of this together and integrate this into kind of continuous integration type workflows. So I'm going to talk about all 4 of these tools today, but just be aware that only 2 of them currently come in the Mobile Studio download bundle. Very, very briefly about each of these tools in one slide. So Streamline's a system profiler. It takes samples from the software that's running, so program counter sampling to see where the software is at any particular point in time, CPU and GPU performance monitoring, and OS level scheduling events for the applications and threads that are running. And we can visualize all of this on a timeline, so we get some overall view of where the system is spending time and where an application is bottlenecked. Is it CPU? Is it GPU? Is it memory? Streamline's also a native code profiler, so we can take PC samples from the software that's running and over a number of samples build up a picture about where the application is spending its time. So you can find hotspots in your native code, identify where you should be investing in software optimization efforts. You can do overall tuning, so you can see for an application, is it spending its time on the CPU? Is it spending time on the GPU? Within those processes, which of the functional units is the critical path? If for shading, is it arithmetic? Is it texturing? Is it memory access, for example? The tool also supports application event trace. So the idea here is that you can annotate your application, so you can demarcate time regions in the profile which represent logical workloads in the application. So maybe you annotate a frame of rendering doing physics, for example, separately from the rendering code. And then on the unified timeline view, you can see how those annotations line up with the other data that's being presented, such as the counter information or the CPU utilization information. So this helps break down the behavior that you're seeing and tie it back to specific application workloads. Graphics Analyzer is a GPU API debugger. So it sits between the application and the graphics driver and captures all of the information being sent into the graphics API, both for OpenGLES and for Vulkan. It can also capture output from the GPU. So, for example, capturing the frame of rendering on a draw call by draw call basis, so you can see how the frame is being built up. In addition, it supports a number of debug visual views, so we can swap in shaders automatically that change how the frame is being rendered. These can show things like overdraw or which shaders are being used to color each pixel. This tool isn't necessarily a performance tool in its own right, but it gives you full visibility of what the application was doing. So it tends to be used in conjunction with a tool such as Streamline to identify where particular hotspots might be coming from. So Streamline might show you that you have very high texture load, for example, and then Graphics Analyzer can show you all the draw calls, which textures are being used, which shaders are being used, and help you identify where that texture load is coming from. The offline compiler is a command line utility for generating static analysis of shader programs. It will give you information about functional correctness. So if you have any compilation errors, it will give you a clear error message about what's gone wrong. And it's also a performance tool that will give you static analysis about the performance of a particular shader for a particular Mali GPU. So in this particular scenario, we can see the shader program costing is being broken down into the 3 parallel pipelines that exist in a Mali T880 GPU, the arithmetic cycles, the load store cycles, and the texturing cycles. These 3 pipelines run in parallel, so you can use this to analyze the critical path and identify which of the dominant resources should be your optimization target for your shader program. So in this case, we can see we have 10 cycles of arithmetic in the longest path to 5 cycles of load store and 8 cycles of texturing. So if we wanted to make this particular shader program faster for that longest path, we'd be looking at optimizing the arithmetic workload because that's the highest workload for the shader program. The final tool is Performance Advisor. And the idea here is to take the data that a tool such as Streamline can generate and automatically put it through an initial analysis to give some very quick feedback to potentially less expert users. So maybe your QA engineer designs a report and the less expert members of the team can pick this up. So for game teams, you might have a few coders and a few QA people, but quite a lot of artists who maybe don't want to understand all the system level detail that tools such as Streamline can show. So the idea of this tool is to show you a high level at a glance view about how well is my application performing, where's the major bottleneck, and on a night to night basis, are things getting better or worse? It is worth noting at this point that because Mobile Studio is designed to be used on release build smartphones, it is somewhat dependent on the phones on the market supporting all the data sources that the tool needs. Currently, Android does not mandate a guaranteed level of data source availability. So you have to have an appropriate device to capture all of the data that we'd recommend. Our high-level requirements are a device which has kernel 4.4 or higher, a kernel perf utility which allows us to access data from user space that's correctly configured with the ARM CPU performance monitor unit, and a Mali GPU that has an appropriate GPU and appropriate driver version. If you don't have all of these on a device, the tools will still work. You will just get less data being exposed. So you don't have to have a Mali GPU. You could have one of our competitor GPUs, such as a Snapdragon Adreno. You'll still be able to do CPU profiling, for example. We do publish a supported device list online, and the devices there are the devices that will support all of the major performance data sources that we would ideally like to see, but other devices may work. To help improve this going forward, we are looking at developing some conformance tests for device manufacturers so they can run this on their devices ahead of time and see which data sources are going to be missing from the tools so they have a chance to correct it before they ship the device. So what overall workflow does this enable? So first of all, it's worth remembering that performance optimization is a data-driven science. So generally you go through a loop of measuring performance, triaging the data to work out where the problem is likely to be, deep dive in to find specific hotspots, identify why that hotspot might be happening in the application code or rendering logic, make an optimization, and then repeat the process. And iteratively, you will improve the performance of the application, making many changes over time to achieve the target CPU load, GPU load, or memory bandwidth consumption that you're aiming for. Because you're iterating and you're relying on data measurement to do this well, you need a consistent methodology and reliable underlying data. If things are moving around underneath you that you can't control, then it's quite hard to actually do 2 runs with a change applied and guarantee that you've made an improvement. This is particularly important for GPU analysis. So the level of abstraction between what the graphics API lets the application specify and how the hardware actually behaves is quite thick. So there isn't a direct mapping of one to the other. Temporarily things get broken up and there's a pipelining effect and things get overlapped. So tooling is particularly important to make this efficient, because if you can't do that translation in your head, you're effectively relying on gut feel to work out what you should be optimizing. Tools can help make that much more concrete. So the kind of technical process that this tool suite enables starts off with something like Performance Advisor running. This does your initial triage, tells you where your major problems are going to be. Is it CPU? Is it GPU? Is it thermal? This can then move into a detailed analysis tool such as Streamline. So you can dive into all of the data that you have access to, counters, thermal information, annotations, and try and work out why a particular slowdown has occurred, particularly which behavior are we looking for. The workflow then forks depending on what kind of problem that you have identified. It could be a CPU load problem. In this case, you would use the CPU profiling features inside Streamline to look at your native code and identify the hotspots in it. If you haven't got native code, that's not the end of the world. Streamline's not a native a Java profiler, and it can't see inside libraries that you didn't develop, but it can at least tell you that there is load inside Java or there is load inside a third-party library, so you still know where to go and look next. If you identify a graphics problem, then you can capture a single frame in more detail using Graphics Analyzer and look at all of the behavior of that application, how the render passes are being constructed, how the draw calls are being constructed, all of the meshes and texture data that's being used. And you can use that cross-correlated with the Streamline data to identify why the hotspots that you're seeing in Streamline are occurring. If you identify a shader load problem, then you can find the hotspot shaders in Graphics Analyzer and then use the Mali offline compiler to then optimize them offline and measure the improvements you're likely to be seeing. So overall, that's the process we're trying to enable. We're now going to look at each of those steps in more detail to try and show how this might work in practice. So the first step we have today, given that Performance Advisor isn't yet released, is using Streamline to perform that initial triage nurse role to coarsely identify where an application developer should be looking next. So the idea of Streamline is that it provides a full at-a-glance view. So the main view you have is this timeline window, which shows all the CPU activity across all the CPUs in the design, CPU counters, GPU counters, thermal sensors, thread scheduling, and if you have user annotations, you'll see those on this time track as well. So you can identify a range where you see a drop in performance, and then within that range, try and identify, is the dominant load going to be CPU? Is it going to be GPU? And if it is one or the other, can we identify which thread is the dominant CPU thread, or within the scope of GPU rendering, which is the main workload that's causing that problem? Is it vertex shading? Is it fragment shading? Is it a particular pipeline inside the shader core? For most content, it's usually very clearly visible, even at this stage, where the major bottleneck's going to be. So you might need to dive into more detailed analysis to find a specific hotspot, but you at least know whether you're looking at a CPU problem, a GPU problem, and if it is GPU, whether it's vertex or fragment workloads. As a very, very brief sample of this, this is a set of scenarios just looking at a small amount of data, which will show you how you might identify where to go and look next. So what we're going to look at for these scenarios is just 3 graphs. CPU activity, so overall how busy are my CPUs, vertex activity, the time the GPU is spending doing vertex processing, and fragment activity, the amount of time the GPU is spent doing fragment processing. This is the scenario that we would generally want to be able to see. So we see a nice regular step, and everything is going idle, typically at a 16 millisecond or a 32 millisecond stopgap, right? So this is something where we're hitting our vsync target, so we're hitting 30 FPS, we're hitting 60 FPS, and we're kind of bound by the display update rate that we're targeting. And this is a well-behaved application. You might still want to optimize it for energy efficiency, but it's not having any major performance issues. In another scenario here, we can see that we still have the CPU and vertex activity coming in reasonably regularly, but the fragment activity is running almost flat out all of the time. If we're not hitting our FPS target, it's pretty clear for this application that we're fragment bound, so we need to go and optimize our fragment shaders or our rendering complexity in our fragment pass. In this scenario, we see a constant CPU load, vertex activity and fragment activity both going idle regularly. So this looks like a CPU active bottleneck, so we're CPU bound. But the graph here seems to show that the CPU is only 50% busy. Those bars aren't particularly high. The trick here is to note that most mobile systems are multi-core systems. In this particular scenario, we have a 2-core mobile phone. If we expand the CPU activity by clicking on the little triangle button at the top, then we see that within this device, we have 1 core running flat out all of the time and 1 core almost idle. So the average load is 50%, but we have a single thread that is our bottleneck. This is quite common in OpenGLES content, where there's typically a single thread that's driving the rendering context, for example. So in this scenario, we have a CPU-bound application. We'd go and look at what the workload that thread is doing in more detail and try and find the hotspots to optimize. A slightly more complicated scenario is a case where no processor is running flat out all of the time, but there's always one processor running at any point in time. So here we see content that's not hitting its frame rate target, and we see oscillation between CPU fragments and vertex in a quite tightly coupled manner. This is typically indicative of API use forcing a flush of the rendering pipeline, causing things to run serially rather than overlapping. If we can make that serialization go away, we get overlap across the processes, things will pipeline more cleanly and keep the expensive hardware busy, and that would generally improve performance. The final scenario is a little bit different. So here we're just looking at the GPU activity. So we have vertex activity and fragment activity that show the amount of time that the GPU is running. And then we look at the GPU cycle count to see actually how many processor clock cycles we're running on the GPU at any particular point in time. What we see here is a system that thinks the GPU is very busy. So the fragment activity, number of milliseconds per second that the GPU is running, is staying very high all of the time. However, we see that the GPU cycles are dropping over time. Now, this is a little bit counterintuitive. Normally, if a processor is busy, the system would keep it clocked up to try and provide the performance that the system needs. This is typically indicative of a thermally bound scenario where the device is overheating, so the system is throttling the frequencies available to try and bring the thermal environment back under control. This is reasonably common on high-end content running on a high-end smartphone, because a modern phone, if all the processors are busy all the time, can generate more heat than it can dissipate. So this is typically indicative of content where you're exceeding your thermally sustainable budget and the device is overheating. So in this scenario, you try and find fragment activity in this case because it's the dominant one and optimize that. But because the bottleneck is maybe thermally related rather than specifically processor related, even reducing CPU load and vertex activity, even if they're not your critical path, would help because it's going to reduce the overall thermal load on the device. So here we can see, even with a relatively small number of kind of data sources, we can start to coarsely work out where to go and look at next. So once you've done this, you can then use the tools to dive into a particular area in more detail. The first thing you might need to look at is the software load aspects. You have a CPU-bound scenario. How do you go and profile that in more detail? Streamline is a native code profiler. It takes PC samples every millisecond and over time can build up a statistical picture of where your process is spending its time. So you can see this initially on the timeline, which we used in the triage phase to see which processes are busy, which threads are busy, and whether the CPU load is indeed a problem. Once you've identified that it is a problem, you can pick a range or you can identify a thread that you care about, and you can use the call path view to look at the distribution of samples across your native code libraries, or if you haven't got symbols, just which library time is being spent inside of. So in this particular case, we have some native code, and we can see the functional breakdown of where time is being spent. In this case, we see 40% of our time is being spent inside the memperf test 2 megabyte function. That's something we might then go and optimize as a leaf function. If you want to dive into more detail, you can view source code and disassembly for single function calls and get a breakdown of where the statistics show time is being spent inside that on a line-by-line basis. Now, obviously, with a modern out-of-order core, the attribution isn't perfect because you have lots of things running in the core in parallel, but it gives you a pretty strong idea where the hotspots might be. Finally, we have the idea of annotations and the event log. So this is where you have software-generated annotations in the code that can be used to demarcate time regions for a single, for each thread that's running. And this will give you a feel for the logical workloads that are running. So in this particular scenario, we've annotated frame boundaries. These are showing up as the red ticks on top of the timeline view. We've also annotated things like the Unity batch system to generate events that tell us when we're scheduling batch workloads inside the Unity game engine. This is entirely customizable, so as an application developer, you can add annotations for any kind of workload inside your software that you would like to annotate. In addition to PC sampling on 1 millisecond ticks, Streamline also supports event-based sampling. So rather than sampling program counter samples every millisecond, you can configure the tool to sample program counter samples on a particular event after a certain number of event counts have happened. For example, you could trigger a sample every 10,000 L2 cache misses on the CPU, for example. This is very useful for cache-aware profiling or bandwidth-aware profiling, because this is a particularly important topic for high-performance cores. As soon as you start having a significant percentage of memory accesses missing in the L2 and going out to main memory, you tend to find the software slows down pretty quickly. Finally, we have annotations. So these are software-generated events that can be used to instrument the code and provide more semantic information about what's running, which you can view on the timeline. There are multiple different types of annotation that you can generate. The first one is a software-generated counter, and this would show up as a graph on the timeline view. The second one is an execution point marker. This shows up as the marks along the top of the time track, which are in green in this particular case. So this could indicate frame boundaries, for example. The second type is annotating execution ranges. So you can mark out a block of time in the thread view to say, during this region of time, I was doing some Unity batch processing, or I was doing some physics. And this helps identify logically what the workload in that time region is. So if you see a high spike in the CPU activity charts corresponding to, say, a physics annotation, you know you're going to have to go and look at your physics code to optimize it. Annotations do support structuring, so you can take annotations and group them into a reasonably complex set of time tracks, and you can encode cross-channel dependencies between them. So if you have data flow across multiple threads, for example, you can show how dependency information flows and how synchronization flows. So in the example at the bottom here, we can see an OpenCL view, which is using these tools to kind of show how a set of CL queues are being issued and synchronized between the CPU and the GPU. If you've used your triage phase to identify a GPU hotspot rather than a CPU hotspot, Streamline's also our Mali GPU profiler. So firstly, a very quick introduction to Mali. So Mali is a unified shader core architecture. So we have counters for each of the major blocks in the GPU. At the top level, we have a job manager, which is the control interface to the GPU, which we can use to see overall workload statistics. We have a level 2 cache, which is used for all memory traffic in and out of the GPU. We have one or more shader cores, which execute shader programs and so on. We have a fixed function memory management unit and tiler unit, which handle some of the more fixed function behavior in the design, so virtual address translation and doing tiling. Inside each shader core, we have quite a complicated processor that's a mixture of fixed function logic and programmable logic. We have fixed function front ends, which are used to create the threads that run inside the shader core. The compute front end is effectively a for loop that will spawn one thread for each compute work item or each vertex. The fragment front end contains the rasterization unit, the early ZS testing unit, and so on. So there's quite a complicated set of behaviors in the front end to decide which fragment should get spawned as threads. And on the back end of the core, we have some fixed function units that will retire tiles back out to memory, rendering the frame buffer tile by tile out to DDR. Inside the execution core, we have a number of programmable units which are responsible for executing the shader workloads. There are multiple generations of Mali core. This particular diagram focuses on the more recent Bifrost architecture, which is currently shipping in the latest phones. We have one or more execution engines. These run shader programs and contain the arithmetic units that say do floating point multiply adds and so on. And on the back end of this, we have a number of fixed function units which are responsible for processing more complex operations which are backed by fixed function hardware. This includes things like the varying unit that will do varying interpolation for a triangle, the load store cache, which handles general purpose memory access, and the texture unit, which handles all kinds of texture access and texture filtering. All of these units run in parallel, so if you're trying to optimize shader core bottlenecks, you generally want to identify which of these units is the one that's the most heavily loaded, and then try and work out why it's heavily loaded. So each of these blocks in the design tends to come with a set of performance counters that let an application developer see what's going on. Can you identify the critical path unit? Can you identify why it's so busy? So the GPU is complicated. There are many blocks. There are many both programmable and fixed function. The workloads that are coming in from the application level are quite complex, abstract workloads. Draw this mesh, please. There isn't a direct mapping from what the application specified to single behaviors in the GPU. One API call can translate into many interacting GPU behaviors. To help debug this, we have many hardware counters, and generally you can capture them all simultaneously. So there are hundreds of counters that you can look at to work out what's going on, how's the memory system behaving, how are my shader cores behaving, how is my tiler clip and cull unit culling primitives, and so on. This gives very good visibility, but if you were to look at just the summary of counters that we export in our public tools, there are simply a huge number of them, and you have to be a reasonable GPU expert to understand all of these. So if you're not, this tends to just turn into a data overload problem. There is so much data being returned by the tool, I just don't know what's important or what I'm looking for. To make this easier, Streamline supports the concept of counter templates. So this is a predefined definition of what counters to capture, any computation based on those counters to turn things from absolute cycles into percentages, for example, and a predefined set of timeline charts which we can use for visualizing these counters in the tool graphical user interface. And this enables a very simple 5-step process. First of all, you have to push the tool daemon to the target. You pick the appropriate template for your device. You capture the data. You pick the same template for data visualization. And then you can analyze that using a step-by-step methodology, which we talk through on this blog in a lot more detail, and I can't hope to cover in this presentation. It would be an hour in its own right. I mentioned earlier that one of the things we're aiming for with the Android tools is to make them easier to use. So one thing we're trying to do for the next tool release is to replace the 5-step process with a 2-step process, which should just be push the daemon to the device, and as long as you want the default template, it will automatically be selected and automatically be used for visualization. So then all you have to do is then go and look at the visualization and work out what's going wrong. My team encouraged me to try and summarize the template in one slide. It's quite complicated. There's a lot of data being presented, but it follows the graphics pipeline in a reasonably step-by-step way. So if you're familiar with the OpenGLES or Vulkan rendering pipeline, we have a set of counters that follows that logic. So you can step-by-step work out where your problem is going to be. So we start off in the template with the CPU activity charts, broken down by CPU type and CPU core. This helps filter out the problems that during triage that might not be GPU related at all. We then look at GPU activity. This shows you the overall load on the GPU and whether it's vertex work or fragment work. Again, this will help, combined with the CPU charts, to identify whether you're vertex bound, fragment bound, CPU bound, or have some kind of scheduling issue. So these 3 charts together form the triage process that we ran through earlier. If you have a GPU problem, we then start going through block by block to see what the lower level problems might be. So the first thing might be that the GPU is running perfectly happily, but it's overloading the external memory system. So GPU is a data plane processor. It will go fast if you can keep it fed with data. So the first set of counters that we look at is just a sanity check how well the external memory system is performing. What's the latency we're getting back from the memory system? How much bandwidth is the GPU requesting? Are we getting any back pressure in terms of bus stalls? So the GPU is requesting, but the bus is saying, I'm too busy. If you see a high stall rate or a high bandwidth rate, which can be contributing to high power consumption, then that would be something an application could go and optimize by reducing mesh complexity, reducing texture size, reducing render target size, and so on. We then start looking at the graphics pipeline. So first thing you will run in the pipeline is your geometry shading. So we look at total geometry complexity, how many things are being vertex shaded, how many things are being clipped and culled. So one of the principal things that an application is responsible for is making sure that the draw calls it sends to the GPU are useful draw calls. So don't send draw calls that are behind the camera, don't send draw calls that are very, very complicated, but only 10 pixels high. So we can see the reasons for why triangles are being culled here. Are they out of frustum? Are they backface culled? Are they very, very small? And so this can help directly map to how well the application geometry setup is working. Most content has more expensive fragment processing than vertex processing. So the first thing you will do here is check the total number of pixels being rendered and sanity check the total number of fragments per pixel that are being requested. So one common problem for 2D games and user interfaces is a very high layer count where each individual layer is quite cheap, but in aggregate, if you add them all together, the total cost per pixel is quite high. We then look at the fragment front-end units. So we rasterize your triangles into fragments that are going to get run through the shader program. And there's a number of behaviors that are important in that front end that an application has control over. The first one is ZS testing. So how many things are being killed by depth and stencil testing? Are things being ZS tested? Are they being killed? Are they being removed by our hidden surface removal scheme, forward pixel kill? Ideally, you want to see things being killed at early ZS, right? If they're inside the frustum and you have a good render order from front to back, then things that are overdrawn won't get turned into fragments. If you see a high percentage of things with the hidden surface removal being killed, that could be indicative of an application rendering things from back to front and generating things that early ZS can't remove reliably. So that could be indicative of a render order fix in the application. We can then look at things going through to late ZS and how many things get spawned into the shader cores. If we're happy with that, we then start looking at the actual shader core workload itself. It is a unified shader core, so the stats you see here will be a mixture of vertex shading, fragment shading, compute shading, and so on. They all run on the same hardware. The most obvious thing that you want to check if you're shader core bound is your pipeline usage rates. So inside the shader core, we looked at a number of the blocks earlier. We have the execution engines for doing arithmetic processing. We have the texture unit, the varying unit, and so on. And you want to identify the most heavily loaded one of those because that's the one that you're going to want to optimize. There are also some workload quirks, particular behaviors that might be important if they're common. So how many tiles are we killing because they never changed? How many warps are we spawning that don't contain a full thread complement? Do you have divergence in control flow across a warp? Finally, we look at each of the pipelines in more detail. So if you see if you're texture bound, for example, we can then look at the behavior of the texture unit to try and work out why the workload is so heavy. So cache efficiency of the texture unit, multi-cycle texturing instructions, and why they might be happening, and so on. So step by step, you can narrow down to a reasonably specific behavior to go and look at in a tool such as Graphics Analyzer. Finally, we can get a breakdown of memory access. So if you have a high overall memory, these charts will help you see where that's coming from. Is it vertex data? Is it compute data? Is it texture data? Templates are configurable. So we provide some predefined templates for different GPUs. But if you want to customize a template for a particular type of CPU analysis or a particular kind of GPU analysis, you can customize them, you can save them out, you can share them with your team. So they're a really useful tool for packaging up a common workflow that your team uses in a form that's very easy to then reproduce. Single click to pick the counters, single click to visualize. Once you've found the rendering issue, you then tend to use Graphics Analyzer to try and debug why a particular bottleneck is happening. It's worth noting Graphics Analyzer is also a functional debug tool. So because you can capture the rendering coming back from the GPU, you can see why it's particularly heavy. So it simply captures all the API calls, all the input resources, all the output resources, and lets a user step through the frame, render pass by render pass, draw call by draw call, and see how that is being built up and all the render states that are being used. So in general, Streamline can show you what's going wrong. Graphics Analyzer can show you why it's going wrong. So this is a typical view you will get. You have a trace outline on the left, which is every frame, every render pass, every draw call. You will have all the API calls that were made, the frame capture for the current draw call that you're on, if frame capture was enabled, a debug view of the vertex data, if it's possible to recreate it, the target states, frame stats, all the shaders, textures, buffers, and uniforms, and so on. So it's a pretty detailed capture of all of the render state that the application's using. So if the API can see it, the tool generally will let you then go and inspect it. We have a number of debug modes that you can use. So the default frame capture mode is going to give you the original rendering that the application requested. But on a frame by frame basis, you can swap in additional debug modes. So you might have an overdraw mode. This highlights fragment overdraw. It can also be a useful X-ray mode. So you can see if something's behind a wall, but it's still being drawn, for example. So it's a visual culling check. We also have shader map mode and fragment count mode, which swap out the shader programs for a simple color map. And this lets you visually correlate what proportion of area of the screen is being covered by which shader programs. So it's a useful means to estimate total cost of fragment shading. It's not perfect. The way it works is a model of the behavior, but it's good as a kind of first pass. Which draw calls, which shaders should I be worrying about? So you might have a shader that's very expensive, but if it's only covering 10 pixels, you may not care too much. It's worth noting that Graphics Analyzer isn't currently a profiler. There's no in-tool direct measure of per draw call cost breakdown. There's no per draw call performance counters. This is a common request. It's something we're looking at, but it's not available today. So you have to use it in conjunction with Streamline and its 1 millisecond samples to give you a feel of which hotspots you're looking for and why. There is a human review process here to try and use Graphics Analyzer to spot deviations from best practice. So we have a best practices guide that we publish online, which makes recommendations about how to use OpenGLES, how to use Vulkan to kind of get the best out of a Mali GPU. And you can use this in conjunction with Graphics Analyzer to spot the problems. Mali Offline Compiler is a shader debug tool. So it provides shader validation and static performance analysis. It supports OpenGLES source code shaders. It also supports Vulkan SPIR-V shaders if you've compiled them already and have a SPIR-V binary. It doesn't understand any dynamic state, so it is just static analysis, but it gives you a good feel for what the critical path is going to be for that particular shader program on a particular GPU. There are some current limitations. It only supports single shader programs, so it's not doing any link time error checking of a whole pipeline. It's not applying any whole program optimization across the whole pipeline. It's currently stateless, so if you have specializations that could have been applied if you have a Vulkan program state object, those aren't going to be reflected in the data. And currently it reports Midgard-like pipeline statistics. So it assumes you have an arithmetic pipeline, a load store pipeline, and a texture pipeline. The Bifrost hardware doesn't quite work that way, so the statistics the tool gives are useful for trend analysis, but the absolute values aren't necessarily representative. That's something we'll be fixing in a future release. Finally, we have Performance Advisor. With the caveat, this is a pre-release tool that's currently in beta, so this is all subject to change. The workflow that we have with the existing tools is basically driven as manual analysis. So a user has to manually connect to the device and capture some data, and then manually do the analysis and route. We think that if we had some automation here, then we can move experts off that critical path and hopefully automatically route the initial triage to the appropriate team to fix. So if we can see that there's been a regression on texturing, for example, and we know there were some changes made by the art team, then we could route that request straight to the art team to say, hey, you need to go and look at your texturing for this particular game. This moves the experts off the analysis path and means they can focus on solving the difficult problems that the automation can't handle automatically. So Performance Advisor is trying to provide a automated triage nurse role. So that initial set of graphs we looked at for Streamline, can we do that kind of analysis automatically? So run a game in a CI system, identify hotspots, hopefully identify a kind of obvious triage root cause, and then route that to the appropriate team, and do it in a way that can be integrated into a nightly continuous integration system, so we can catch major issues early. So the approach here is to capture the data in Streamline. So it's the same tool. If you want to investigate in more detail, you can then open the same data file in Streamline, but analyze the data through a automation process that produces a report. And this report should summarize the obvious triage process automatically, without requiring a human involved to do that analysis. At a high level, it will give you a breakdown of your costings, and an average FPS for the application, so you can see if you're getting better or worse. It will try and break things down by region and tell you which regions are CPU bound, which regions are vertex bound, and so on. So for each part of your game, it will have some root cause to go and investigate if it's not hitting the FPS target. We do have region labeling, so this uses annotations in the game to identify different parts of the test scenario. So you can identify logical behaviors from the data directly from the report, without having to just look at time and work backwards. So here you can see clearly the loading screen is CPU bound. The intro, once it's loaded, is actually hitting its 60 FPS target. Then for each region that we identify, we do a similar breakdown. What's the average FPS? What's the average utilizations of the CPU and the GPU? And if we identify a problem, provide some links back to advice where you can go and find out more information. And the idea here is that we can integrate this automated analysis into a CI flow, and then the team can just get these regular reports without needing someone to manually go and repeat the checks all the time. So it pushes your expensive resource or your limited resource, your graphics programmers or technical artists, off the critical path, and hopefully gives feedback straight to people who don't necessarily have the expertise themselves to do the analysis. Finally, we're going to very quickly look at our roadmap here. So this is the kind of thing we'll be working on over the next 12 months for the next tool release. So first of all, the big thing we're pushing is ease of use improvements. So historically, our tools have been designed for silicon partners and device manufacturers. How do we make them easier to use for an application developer audience who don't necessarily have the same experience? This is going to be a mixture of workflow simplification, but also updated documentation and some better tutorials on our website so that people can learn how to use the tools more easily. We're going to look at increasing the number of devices that we officially support. So we have the new Samsung Galaxy S10 and the Mate 20 device that we need to go and test and make sure they work as we expect. I also mentioned earlier we're going to look at rolling out a conformance testing program for silicon partners and device manufacturers, so they can test ahead of time to make sure their devices are going to work well with our tools. The Performance Advisor tool is in beta, so if you're interested in signing up for our beta program, you can sign up on our website. We will be looking at improving the Mali offline compiler to solve some of the limitations I flagged earlier. We're also looking at switching our current graphics analyzer tool to RenderDoc for Vulkan API debug. So if you have any feedback about or experience on RenderDoc, please get in touch. And the idea here really is that there are many API debug tools on the market. There's nothing specific about OpenGLES debug in graphics analyzer, for example, that wouldn't be true on another GPU. So we kind of want to focus our efforts on where we're adding Mali specific values such as performance analysis. So building on top of RenderDoc should let us give that kind of tooling more quickly to our users. Finally, we're kind of looking further out at potentially an even better way. So we've mentioned Performance Advisor for doing that initial automated triage, but if you find the GPU problem, how do we provide very specific feedback within the frame of rendering to identify very low-level improvements an application should make? So the idea we have here is to have a tool that will take a frame of rendering with data from both Streamline and Graphics Analyzer and automatically provide a very low-level report about best practice deviations and recommendations about how to improve performance. This should move the experts even further down the line towards solving difficult problems rather than identifying difficult issues. If you want to download our Mobile Studio, it is available online free of charge on our website. Thank you very much.